What this Atwood machine thing is going to allow us to do is, one, deal with, or how do we use, or why do we use free body diagrams, and why are they useful? But two, start to use Newton's second law with free body diagrams together, okay? And you get your first experience with an Atwood machine, which is really important because, like I said, you are going to have 5 million of them in the next, 4 weeks, 3-4 weeks, okay? You and Atwood machines will become best friends. You'll be dreaming about Atwood machines. You'll be going to the gala for gifts next week, and you will want to give a young child an Atwood machine so they can perform their own Atwood experiments, okay? That's how much you're going to know and love Atwood machines by the time we're done with this, okay? You are going to put on your Christmas list an Atwood machine, or pulleys, ropes, and weights, so you can do that, okay? So what I would like to do is I want to know what is the acceleration of this system in terms of M1 and M2. So essentially, I want to find what is the acceleration of this whole thing in terms of quantities that I know, okay, that don't have to be calculated, right? So I know that M2, I can put it on a scale, right, or it's given to me. M1, the same thing, right? I don't want to know it in terms of any forces inside of here or any sort of other interaction, just in things that I can directly measure, right? Because that's the most simplified way that we can do it. And you will get you will get multiple questions like this on the test. You've already done some of them, okay? So we've got M1 connected to M2 by a frictionless rope. Very important that this, a massless rope. Very important, right? Because if it did have mass, that would change the amount of force that was pulling on it as the system moved. Also, the pulley is frictionless, right? So there's no resistance that builds up in the pulley as it spins, okay? So those are two really important things. And the last thing that we'll deal with for now is that this table is also frictionless, okay? Make sense? Okay, so the first thing we're going to do is draw a free body diagram for M1, for both objects, okay? So for first, M1, if we look at M1, always the simplest one is the weight, right? And then we have the normal force, and we'll call it N sub 1, right? So we know it's mass, the normal force for mass 1, okay? And the last thing we have is the tension that is pulling on that block as it goes. Well, we think it's going to go to the right. It's always a great question that you'll see. You know, if we let go of the system, we let go of M2, will the block actually move, right? Will it fall? We'll look at that later, okay? So the next thing we've got, are we done here? Is this good? Right? Right, there's no friction, so yeah, this is a good free body diagram, right? We're good to go. Now for M2, you see how I did red box, red ink, right? Purple box, coordination. Ekman, it's cool. You can. That's good. Yeah. All right. So, what about M2? Wait. All right. So W equals M2G, right? And then we've got the tension going up. Okay. So, let's wait a moment. We'll get there eventually. All right. We good? Well, good. All right. What I'm going to do, just because it looks like they're different, I'm going to call this T2. And I'm going to call this T1, right? Because it's the tension acting on 1 and the tension acting on 2. Make sense? Okay. Awesome. All right. So we've got these two pictures are going to be our guides. From here, in our knowledge of Newton's laws, we can find out what this acceleration is. Okay? The last thing that I'm going to mention is, you see how I give it like this curly arrow with a plus sign in it? So what we're doing is we're saying that anything that moves like this, right, is in the positive direction, and anything going opposite that is in the negative direction. Follow me? That's going to be our sign convention. Just how like normally we say like up and to the right is positive and down and to the left is negative. In this case, for Atwood machines, we need to have this curving, right, this circular sign convention. Okay? All right, so let's start. Let us begin. All right, you can't see, I can't see them, but you can see the free body diagrams. So first of all, this is a hint where to start. First of all, what plane is all the action taking place in for mass 1?
On the table?
Okay, so X or Y, I should say.
Y. No, X.
X, right? All the action, all the good stuff is taking place in the X direction, if you look at our picture, right? So just leave Y alone. Leave it alone. Don't do it. Right, Sirius? Don't do it. Okay. So let's leave that alone. So I'm going to start with our friend, the second law. And we are looking in the X direction, correct? So we're going to leave that there. Okay? All right. So if we look at that, we've got the tension, correct? Right? That's the only force acting in the X direction. And it's acting on M1. And can we say that the X acceleration is really all of the acceleration? It's the total acceleration? Okay. So I'm just going to call that A. It would not be wrong, but it would not allow you to solve the problem. Okay? Because you'll see in a second when we get over here, you have an AX and an AY, and they don't like each other. You know what I mean? Yeah. Okay. Can we go any further with this? We can?
Mass, right?
Right. Well, okay, so we could divide by the mass, but here's the thing. This is not something I can directly measure, correct? This tension in the string? I can't directly measure that, right? I can put the blocks on a scale, get those masses, but I can't directly measure this tension, so I need to find a way to get rid of it. All right? Make sense? So here's something I don't know, here's something I don't know, and we've only got one equation. Should we quit? Don't say yes. Right? No, we don't want to quit. We can't quit. So I've got two unknowns in one equation. What do I need to solve this equation? Another equation. Yes, I need another equation. Well, it's a great thing that we have a second block. Right? The second block is going to give us that other equation. All right, so we've got the sum of the forces. In this case, it's in the Y. Right? Awesome. So we've got these two jobbers here. Looking at that free body diagram for M2 and only M2. All right? We have the weight, right? The weight of block 2, correct? And we have the tension, 2, right there. We should call that ones and twos, right? And that's M2. Could we say now that the acceleration of the Y block, of the second block, is also the acceleration of the entire system? We could, right? So let's call that A. Right? See, Bobby, that's why it's important to call them, to leave it as that, not X and Y. Okay? Awesome. All right. This is not quite done, this side of the equation, right? If we're looking at our sign convention, right, so that anything causing it to go like this is going to be in the positive direction, does the weight, over here, does the weight get a positive or negative sign? Yeah, it's going to get a positive sign, right? Because when this pulls, right, it's going to cause that pulley to go like this in the positive direction, right? What about the tension, T2? Negative, right? Negative. Because it's going to cause the pulley to go in the opposite direction, which we deem to be negative. Okay? So let's leave this guy positive and make that guy negative. Okay? All right. I want to make this a little more simplified, a little more, not generic, but again, things that I know or can measure. So weight 2 is really M2G, right? Because weight equals mass times gravity. Okay? All right. Now, T2. Newton's third law. Every action, there's an equal and opposite reaction. So the tension pulling mass 1 is also the same tension pulling mass 2. Are we okay with that? So instead of calling it T2, could we just call it T? We can. Okay. And then we still have M2A. Okay. So now we're in a really good place. What do we got? 24, you said we're out? No one knows? 30, 32. Oh, perfect. All right. So real simply, the tension is going to be equal to M2G minus M2A. Correct? All right. Now again, Newton's third law says that the tension pulling it up and the tension pulling the other block to the right are the same, right? Just opposite directions. So I can take this and I can plop it in here. Okay? So when I do that, I've got M2G minus M2A is equal to M1A. Okay? So let's do a little bit more work. I've got M2G is equal to M1A plus M2A. Correct? Okay. I'm going to take all this so I get more space. I'm going to put it over here. Okay. So M2G is equal to A M1 plus M2. Okay. So then A is M1 plus M2 divided by M2G. There you go. Did I miss something here? I flipped it, right? I apologize. M2G, M1 plus M2. Okay? So this would be our straight generic equation for the acceleration of an Atwood machine. Or this is actually technically a modified Atwood machine. Okay? What do you think? Are we okay? Yep. Okay? It's not too tough, right? And this is actually probably a little bit more complicated than what you'd want to start with. But in terms of just using Newton's second law in free body diagrams, do you see how free body diagrams pretty much put everything into place for you? Right? Okay, so that's why it's really, really important that you draw good free body diagrams, accurate free body diagrams, because they're going to essentially do all the work for you. Right? Because once you do this, right, you set up these two equations, it's just algebra. Right? It's just rearranging equations, okay, which isn't too difficult. So imagine we take our masses. We have M1, right? And I'm going to take these masses, and really they act as one thing, one unit, right? Right? The tension in the rope stays the same, so whatever happens to M2, it affects M1 directly, right? And really, if you do something to M1, it's going to have an effect on M2. So if you pull down on M2, M1 automatically experiences something, right? And if I pull on M1 going the other direction, M2 automatically goes up with it, right? So really, while they're two separate blocks connected by a string, really they act like one unit. Does that make sense? Right? They act like one unit. So let's pretend that they are one unit. Okay? So let's pretend that they are one unit, and I'm just putting this circle around it to imagine that they're one big thing. Okay? So anything, what happens is anything inside this unit, or really what we call it a system, anything that happens inside this system has no effect on the system itself. Right? So if M1 and M2 are pulling on each other, it doesn't affect the motion of this system. So that's great because now this tension, whatever happens in one direction happens in the other, and inside the system it cancels itself out. Follow me? Okay? So anything that happens now inside of here, it's an internal force. It doesn't affect what happens to this thing as a whole. Follow me? Okay? So all we have to do is look at what are the forces now that are external to this thing as one big unit. Okay? So if we think back to the drawing that we had, right, of the actual situation, what forces are being applied to this system as a whole that are external to this thing?
Gravity.
On which one? Or both of them? What would you say?
M2 would be the most effective.
Right, so M2, right, this would be the weight on block 2, is the force that's outside that's causing it to move, correct? Right, if we look back at our drawing that we have up here, our diagram, the downward pull from M2 is what's causing everything to move, right? And that's outside, right? That's gravity pulling down on it. That's Earth pulling down on M2, right? The table's frictionless, but if we had friction here, right? If there was friction on M1 in the table, then we would have a frictional force going that way as well, correct? But the only thing acting on, again, this thing as a whole is the weight from mass 2. Okay? So let's draw a free body diagram of what it looks like. We have the weight of the system itself, right? So how would we write down? We can't just write mg, and we can't write m1g. What would we have to write? If we're looking at this as one big thing, how would you categorize the weight? M total? Yeah, M1 plus M2, right? Yeah, so it's M1 plus M2 times gravity. That's the weight of the whole thing, right? And then there's a normal force acting on the thing by itself. And then we have the weight from 2 that's pulling the whole thing, right? And that's equal to M2G. Are we good there, Dashni?
So weight usually goes like straight down, but because M2 would be like pulling the system this way.
So I'm just calling it because we put everything in a line.
Oh, okay.
That's why we're saying that it's
okay.
right. We could draw it like at right angles, and W2 would be going down. But in terms of just solving this and visualizing it, we can just draw it like that. Okay, Grace? Right. But in the long run, it's not going to matter, right? It's not going to have any effect on us solving for the acceleration. If we were worried about the friction, if friction was involved, then this would be much more important. Okay? Awesome. So, let's do the same thing now. So we have the sum of the forces is equal to MA, right? So the net force acting on our M1, M2 system is equal to the mass times the acceleration of it. Okay? So the net force acting on it is weight of 2. Right? Now what about M? What does M mean? What is the M we're talking about? Right, total mass, right? The mass of everything in this case. So this is M2 plus M1 times A. And we know that W2 is M2G times A. So if we just write it over here so we can see it, we get that A is equal to M2G divided by M1 plus M2. And that's exactly what we got the first time, correct? Okay. So what this that really does is it just it's another way of looking at it. It's a different point of view, right? It's significantly faster. Okay? So sometimes something like this, it's easier to go this way with it. We could do the same exact thing if we had like 3 blocks, like in the question that we just answered, where we had, a block here and a block here. We could do the same exact technique. Only now we would have a W going that way as well that we'd have to take into account. But we do the same exact technique. Okay? We could have a block inside here. Let's add a third block. Right? If we do that, really the only thing that changes is now this is like M1 plus M2 plus M3. Okay? So it's pretty powerful. If you want to do 3 free body diagrams, have at it. Right? But this technique at least allows you to get through it a lot more quickly. And if you have to solve a free response question where you've got a situation like this and you have to answer a question like this, it saves you a lot of time.